Monday, April 7th. This is CS 746. Today's lecture is on classification 3. It's a relatively short lecture, so I'm hoping to have time to go somewhat over the midterm afterwards. So before I decide to talk about the midterm, anybody in here that hasn't taken the midterm yet? Anybody online that hasn't taken the midterm yet? Okay. So as long as everybody here has already taken the midterm, we can talk about the midterm. Yeah. Otherwise, we don't talk about Fight Club. Yeah. Anyhow, so classification 3. Today's topics. We've gone through several types, but now we're on the last 2, which is decision trees and random forest. And imbalanced data sets is a separate lecture that sometimes I try to cram these in together, but today I'm going to just go ahead and do this and then talk about a little bit about the midterm and what the answers were and stuff like that, and what we're going to do about people who felt like they didn't score high enough on that. So my brain trying to think of an idea for deep learning paper, from a researcher, no ideas. Coming up with deep learning memes, excellent, right? Data scientists, well, you're training your models. This is the part of data science where you just like set it loose, let it go train itself, and go off and have a nice walk, sit on a bench, something like that, right? So anyhow, decision trees. It's simple enough. Here's a simple binary decision tree. Should I exercise? Do I want to go for a jog? No. Well, am I just being lazy? Yes. Okay, get up and go. No. Well, if you're not sick, you should still go for it, right? But if you're sick, okay. Yes, did I get enough sleep? No. You get enough sleep, skip it, get some more sleep, right? Sleep is more important than anything else, right? Well, maybe food is more important than sleep, but yeah, who knows? Anyhow, so that's our decision tree, right? Just we got a tree, we got nodes, we branch it to the bottom, great. There's root nodes, child nodes, leaves. Supposing we want to have a class, and we're trying to do some sort of a classification on our class, right? And so we can go ahead and do different splits. We can maybe take our class, we got 30 students, half of them play cricket, right? 50%. Maybe we go ahead and we say, let's divide into females and males. And we see that, more the males play cricket than females, right? 65%, right? We're doing our discussion here. So we're trying to find out, how to decide which students play cricket, right? Without knowing that up front. So we're trying to build a decision tree on that. So that's our target, right? And we're trying to find other ways. Split on height. And well, we see that we got play cricket is 42% out of 12, 56% out of 18. Here we got split on the class that they're in, lower class, upper class, right? 9th, 10th classes, 14 students in the lower class, 16 students in the upper class. Some of these divide more evenly than others. None of these, well, one of these, the gender split, is better at our target prediction, which is, do they play cricket, yes or no, right? But our decision tree, we just kind of keep on going through down and to lower levels, right? So we've got 2 types of decision trees we can deal with. We can do a categorical, or we can try to do a continuous one. And a continuous decision tree on a binary split where you're doing categorical splits at every level sounds a little weird, right? But you can make it work. So, again, with a target categorical variable, the student will play cricket, yes or no, right? So in the tree, just like every tree, we have the root, the trunk, as we could, or some trees have trunks. This one doesn't, just has a root, right? And it immediately splits into branches. Internal nodes are called decision nodes, where we split again. When we reach a node that does not split, we've come to a core node that has got either all correct or all incorrect answers, all yes or all no in it, right? We call that a terminal node. Or we can have a node where we have below a threshold for errors, right? We can define an error, right? Pruning. If we decide that our decision tree has gone too far and it started to memorize things, we could start pruning off terminal nodes and say, we'll accept a little bit of impurity. We don't need these 2 terminal nodes, right? Our branch or subtree is the entire set of the tree. The parent course node is the and the child relation is always the parent is where the decision is made. The child is the subnode of the parent. Simple terminology. Weather. Is it sunny, cloudy, or rainy? Right. Humidity. High, normal. Yes or no. Rainy. If it's rainy, was it windy? Yes or no, right? And we're trying to do some decision, and I think this is harking back to our earlier example of, where we're going to try to look out the window, look at the weather, and decide, do we expect to see the kids playing, cricket or baseball in the lot outside, right? And so there's our decision tree. We look at the weather, we see what does it feel like, and then we go out there and we make our prediction, right? Entropy. The concept of entropy in physics is a measure of disorder in the universe. In information theory, the concept of entropy is how much or how little you know about your data set, right? So entropy in decision trees is how we measure the impurity of the node. The more consistent all the answers are inside that node, right, the better our data is, right? So the less the entropy is, the less the impurity is. The degree of randomness is another word for impurity. How random our data is. If we do a perfect pure subsplit, right, whatever our target variable is, a pure subsplit will have all of this side will have yes answers, all of this side will have no, right? So that's a pure subsplit. A poor entropy subsplit with high entropy is going to have a lot of basically 50-50 in that node, right? Suppose a feature has 8 yes and 4 no when we start. And it's a little tough to see those on the slide there, but that's 8 yes and 4 no. We find feature 1. We split on that. And now for our target, we've got 5 yes and 2 no's on one side, 3 yes and 2 no's on the other side. That's not a pure split because each of those nodes is still mixed. So we go to a next level in our decision tree, find another feature, we split on that. Maybe in this case, we'll get lucky and we get, 5 yeses on one side, 2 no's on the other, 3 yeses and 2 no's on the other side. And so now we have purity is 100%. When we have 100% purity in our node, no entropy, we know what the information is, we can say that's definitely going to be a leaf node, right? So what we want to do and our decision tree is to find at each level of the decision tree the best attribute to pick for our decision or for our split, right? So we need to have some sort of a metric. Always important to have a metric, right? And we'll use the attribute selection measure. And we can then easily select the best features based on our ASM. There are 2 techniques for ASM. There's one called information gain, and the other is called the Gini index. Right? Information gain measures the reduction of uncertainty. It's just the entropy of the full data set, right? The entropy of the data set given some feature. For any feature, it tells us how much information that feature provides us. So following the value of the information gain, they split the node, and the decision tree building is done. So basically, we got there, we look at all of our features. How good is this feature at deciding between yes and no on our target variable? How good is this other feature? So on and so forth. How much does it decrease the entropy of our overall data set? And we pick the one with the biggest decrease in entropy. Do that at each level, right? So decision tree always tries to maximize the value of your information gain. And you notice we talk about information gain here again. This is information theory. It's a branch of mathematics. Was developed during World War II. And shortly after, and all the terminology we use like every day, we throw the word bit around, right? When we talk about binary information digits, that came out of information theory in the 1950s, right? And so all these metrics, so much of what we do today is based on information theory, understanding the information value versus the entropy, so on and so forth. We discussed that in the other class I teach, Advanced Topics of Data Storage advertisement. Okay. So the decision tree always tries to maximize the value of information gain, right? So we always pick our node with the highest information gained at each split. Another way to do it is do what's called the Gini index. Gini is the name of an economist who came up with this metric originally to describe income inequality in countries, right? And would say, what's the difference between the richest and the poorest people in this country? And this metric then was actually kind of, I don't know if he came up with this idea and realized it applied in two different areas, or if someone else picked it up and says, hey, this is a great metric, but we have two completely different things. If you start talking to an economist, they'll talk about the Gini index, and the US has a higher Gini index than this other country and stuff like that. But in decision trees, the Gini index is simply measuring the purity or the impurity in creating the decision tree. It's kind of the same idea, how homogeneous income is versus how unhomogeneous it is, right? So how much randomness we have in the nodes, right? So we're using a classification regression tree algorithm, CART, it's the index or the acronym for it. And basically what we want to do is say that we have a Gini index with a low value is what we prefer to 1 over the high Gini index. This will create binary splits, and then we'll use that index to create those binary splits. So basically the index is calculated using this formula. We take the sum, we've done some split, we've got our class down here, we have the probability of that object being in that class, right? We sum up for every object the probabilities. This is not, simply a single metric. We can be looking at multiple different things. We subtract that from 1, we get a measure of the impurity in there, right? So we want the lower impurity in our nodes. When do we stop splitting? Well, the thing to keep in mind is that a decision tree, if we don't tell it to stop, will go until every single node is pure, right? Every single leaf node has only one answer in it. There's actually a danger of overfitting in this case. Real world data sets have lots and lots of features. It would lead to lots and lots of splits because you keep splitting on more and more features. That would give you a huge, expensive, overfit tree. On your training set, it would do great, right? But when you try to run your test data through it with this not seen before, you would have fairly bad accuracy in that situation. So a basic idea in our decision tree algorithm is we want to select our best feature, measure that attribute, make that a decision node using our ASM, split it into smaller subsets, keep splitting into recursively smaller and smaller until we reach a termination state. And that is the termination state 1 is all of the tuples in that node now belong to the same attribute. It's a pure node. Or we've run out of attributes, or we've run out of samples, right? So those are the 3 obvious stopping conditions, but we can stop sooner as well, right? Now, if we want to avoid the risk of overfitting, we can go ahead and start adding some, and these are arguments on the Python sklearn decision tree method. We can say, just stop when our tree reaches a certain depth, right? We go down 4 levels and quit, right? So there's a max depth. Min depth is not a valid stopping criterion, right? Min depth is like, keep going, right? Minimum samples in the leaf, on the other hand, this requires a minimum number of samples at the beginning of the leaf node. If you get smaller than 3, stop, right? If you try to flip that max samples leaf, that's also not a stopping criteria. In every of these cases, if you just kind of invert that max to min or min to max, you'll see that it doesn't make sense as a stopping criterion. But in these cases, you're going to split till your leaves are small enough, and then you're going to stop. Your minimum samples to be able to do a split. So if you have too few things to do your split, you're going to stop. You're not going to make it any smaller than that, right? Maximum number of features. You have 10,000 features to look at. I'm only going to look at the 500 best and then quit, right? So those are some of our parameters that we can use to when to stop splitting our decision tree. So there's two ways to hit our decision criteria. First of all, we can just go ahead when we reach that max depth, we can say stop, or we can do what we call post pruning. So we can start, by growing, we can just stop growing the tree when we reach our termination, or we can go ahead and build out a full tree all the way down to every single node being perfect. And then we can start looking at our nodes, see how useful they are, and start splitting or pruning them, combining things back up until we get to our criterion, right? So we got pros and cons for decision trees. The first part is that it's easy to understand. We're just doing a flow chart. Yes, no, inside, outside, in group, out group on every decision. A lay person with no analytical background can easily understand and follow a flow chart. Doesn't require any statistical knowledge. When you draw it as a tree, it's intuitive and easy to understand. Your users can understand and relate to the hypothesis that you're making in your testing, right? It's very useful in data exploration because it's one of the fastest ways to identify your most significant variables and your relations between the variables. If you've got a variable that doesn't give you any improvement in your Gini index, it's not a useful variable, right? We can create new variables or features with better predictive power, right? There's less data cleaning required in a decision tree compared to many other modeling techniques, right? We start doing like principal component analysis. We have to normalize everything. We have to make sure it's all scaled the same. We have to, in some cases, start doing kernel tricks and so on and so forth to be able to get our support vector machine working, things like that, right? So we have less data cleaning. We're just letting it make the decisions, right? It's got minimal influence from outliers. The data type. Some algorithms only work with numeric data. Others only work with categorical. Decision trees can handle both. Doesn't care. It's also non-parametric in that it doesn't make any assumptions about the distribution of your data underneath, right? It's just looking at the data, making classifications, okay? Cons, on the other hand, the most obvious con is that decision trees really want to overfit, right? If you don't stop it soon enough, it will overfit your algorithm. So that's why we have to set constraints or come back and prune things after we build the tree, right? It's not great for continuous variables. You can do classifications. In other words, if you wanted to like arrange this class by height, that's a continuous variable. We just sort everybody individually pairwise, right? If we try to do that with a decision tree, we either have a tree that goes down and puts everybody in their own leaf, or it has clumps of people that are approximately the same height, right? So it loses some information when we take that continuous numerical variable, we put it into categories. Okay. That parenthesis needs to go away. We're going to discuss that in the context of random forest, though. Okay. So decision tree. It's simple. It's fairly quick, but it has some serious cons. Is there any way we can improve it? And the answer is yes. Welcome to the forest. Here's a random decision tree. Here's another random decision tree. That's what a random forest is. It's a versatile machine learning method capable of performing both regression and classification tasks. I'm pretty sure this guy is from the IT Cred, if anybody ever saw that. A guy with a weird makeup on there. But it could be also, yeah, I don't know, whatever that could be. Maybe it's a movie that I never saw. Anyhow, so random forest can do both regression, classification. It can do dimensional reduction. It can handle missing values. It can handle outlier values. Other essential steps. It's an ensemble learning method in that we take a weak algorithm, a weak model, which is a decision tree, and we combine several of those weak models together, and we end up with a model that's more than the sum of its parts and very powerful. Okay, so if it sounds like magic, it's because it is, yeah? Oh, decision trees isn't good enough for you. Tell me more about random forest, right? So if you can't think of a good algorithm, try a random forest, right? So if you're sitting there and you're like, I'm just a stump, I don't know, this Linear regression is not working for me, right? Try a random forest. Client asks for stepwise regression. We deliver a random forest analysis. Decision trees all the way down, right? They make predictions by going through each and every feature in the data set one by one is what a decision tree does. The random forest, on the other hand, takes a collection of decision trees that individually use random subsets of our data set, random sets of features, random data points, right? So the random forest takes a prediction from each and every decision tree in that forest, and then based on a majority vote of what the decision trees say, it gives you its output, its prediction. Single decision tree, random forest. Pretty straightforward, right? Anyhow, we're just doing different classes over here. We're doing different classifications of things. So given n cases in the training set, we take a random sample of these n cases with replacement. So we take out some subset. We build a decision tree with that. We put them back in. We take out another random subset. Could be overlap, maybe not, right? We just build a number of these random subsets to build a tree. Given m input variables or features, right, we select some number m less than n, such that each node, variables, yes, input. M variables are randomly selected from our full feature set, right? So of our feature set, we take, again, a small number of samples, a small number of features, and we build a decision tree. Use the best split on these m, and then we split the node. And while we grow the forest, every tree has small m features in it, right? So all these decision trees are about the same size. We grow each tree as large as possible. We don't prune anything. We just let it go on. If it overfits, that's fine, right? Because this tree might overfit this feature, and this other tree might overfit a different feature. And between the two of them, or three of them, or five of them, we'll get some that we'll get a good actual majority vote out of it, right? So we predict our new data by aggregating the predictions of all these n decision trees, right? Using either majority vote if we're doing a classification, or if we're doing a regression, we take the average of the outputs, and that gives us a regression number, okay? There's actually a link here at the bottom of the slide if you want to go read up more on it in your spare time. It's probably a useful thing to check out. So the sampling, the cool thing about decision trees or random forests is we can use what's called bagging or bootstrap aggregation. Because every model, when you build a machine learning model, you need to have training data and testing data, and you need to keep those separate, right? And in some simple models, you actually have to, up front, you have to take some of your data, you set it aside, that you say, this is my test data, right? When we do k-fold cross-validation, we can find ways of saying we're going to feed for each, portion that we do it, we can, present this portion as training set, and this portion is test set, and then mix it up and have different pieces of the data, right? So we can do that same thing with a random forest, right? So we take in each decision tree, we have the sample that's in the bag, right? That we use to train that tree, and then we have all the subset, all the data that's not used for training that tree is an out-of-bag sample, and we can take that out-of-bag data and use that to test the error estimation for that particular decision tree. And then when we start looking at this, people did studies and they determined that the out-of-bag estimate is as accurate as setting aside a completely separate test set, right? So the cool thing about random forest is, if you want to, you can use your entire data set to train your model, because each individual tree in your random forest is only seeing its own little subset, right? So the out-of-bag error removes the need for a separate set-aside test set, which is pretty cool. So pros and cons of random forest. It can do both classification and regression. because it's doing this regression by calculating an average out of multiple different decision trees, you can get a pretty good approximation of a floating point number out of it, right? So it does a decent job at regression tasks, right? It can handle large data sets with high dimensionality. You can have thousands of input variables, and you can identify the most significant variables. So it is, in fact, considered a dimensionality reduction method because it can figure out these trees are more useful than these other trees, right? The trees with higher or lower error estimates, right? So it can output an importance of your variables. When you run the algorithm in Python, it'll give you this feature is more useful than this other feature, right? It has methods where you can effectively estimate missing data, maintain accuracy when you've got a large chunk of your data missing. So it can handle missing values. That's nice. It has methods for balancing. And again, of course, the way it can do this is some of your trees don't need that data, right? Other trees in the forest need that data. They're just not going to work when you try to run them on that missing data, right? So you get parts of your forest will not respond when you have missing data. Other parts will still respond, right? It has methods for balancing the errors in your data sets where your classes are imbalanced. Imbalanced data set is a pretty serious issue. You need to know how to deal with it correctly, because if you don't, you're going to get wrong answers, right? You can actually use a random forest with unlabeled data, which will give you an unsupervised clustering algorithm and give you views of the data and outlier detection. So you can actually use the random forest. Now, it might take a while. You might set it loose if you don't have the latest GPU in your computer. It might take it a while to run this and give you some useful information. And you can go off and do something else and say, I'm working hard while you're out there enjoying a snack at the food truck outside here, right? So, cons of random forest. Again, it's better at categorization than it is at regression. So, it doesn't give you precise continuous. It gives you an average, right? It's better than a decision tree, but it's not as great as an ordinary least squares regression if you have truly numeric data. It can't predict beyond the range in your training set. It can only make predictions based on what it's seen in the data set. If you've got a lot of noise in your data set, it might overfit because it actually doesn't know that that's noise and will try to interpret that noise as possibly useful information, right? And finally, the biggest problem is that it's a black box. You're setting it to work. You're telling it, go ahead, do this, and you don't even have control. You try to explain the random forest to a person on the street, and they, not quite sure what you're trying to tell them. At best, you have control over your hyperparameters, different parameters. You can try different random seeds, things like that, right? But you don't really have very little control over what the model actually does. Closing in on the end of this lecture right now. So here's an output example where we ran a random forest. And from my perspective, the data set that this was run on is long lost. All I have is this slide. So if someone wants to go out there, I've done the image searches for other data and found out where the source came from. Haven't succeeded with this one yet. Maybe I should try it again. Maybe things are getting better, right? Ask ChatGPT where this picture come from. Anyhow, this is a data set where they're trying to figure out whether to hire employees or not, right? And so you got some of these down here, like, as a mobile verified zone and so forth, and those are not useful in predicting employee, success. Things. There's loans. There we go. Okay, maybe that's it. Who knows what this is? I don't know what this is, but it's obviously we're classifying something to do with money or jobs, something like that. And it can tell us that who you work for makes a big difference on this particular feature. Where you live, things like that, is a lot more important than things like, your device type or your gender or things like that, right? So, whatever that is telling us. Last slide, believe it or not, in this lecture. It's a short one. When the random forest outperforms your support vector machine, was the greatest thing, all right. And it was just like, they're saying you can't read it hardly, but it says, I mean, trees, everywhere trees, what the hell is this, right? So, you do lots and lots of math, lots and lots of floating point to do your support vector machine. You're trying to map everything down to a lower dimension, everything like that. And then you go out there and just crank a random forest, say go for it, and it comes back and gives you a better model. And that is the case there. Random forest is amazingly effective. So if you haven't tried random forest models with your project data, give it a shot, right? If you don't know what else to do. And again, you do that right, you get an output that tells you this feature is more important than this other feature. And then you can turn around and use that to fine tune your model, refine it, get better information, right? Okay. That was classification 3. So I'm going to stop recording now.